Anyways, okay, so hello people. Today we're doing quantification of exercise and calibration and different measures that we would use in this field to be able to quantify exercise. This typically is the most boring lab in the semester, but I like to make it the most fun one because it's my favorite and because we have a lot of physics in here. Has anybody here taken physics already or no? Physics 1 is all I need. It's all I care about. I don't need magnetism and all that stuff. It's not fun. But anyways, so the physics part of our field especially, like I was telling you guys at the beginning, we have different kind of, you're going to take different things from whoever teaches this class, right? Like I was telling you how, Wei teaches this differently, Jesse teaches this differently, and I teach it differently. I use it a little bit more in the sense of, again, strength conditioning, sports science. And so a lot of the metrics and measures in that field inherently are going to be like very physics-based, right? Talking like, mass, acceleration, velocity, power, force, work, distance, time, a lot of these things that are very, quantifiable, for lack of a better word. So the first thing we get into is a little bit of what it is, right? So the first law of thermodynamics states that energy cannot be created or destroyed and only converted from one form to another, right? If you've taken any sort of like basic chemistry, you could probably remember something like that. In exercise physiology, this involves a form of converting stored fuel into energy, or, fuel energy and converting that into work of some sense, right? The energy being what? What energy do we use to do stuff? What energy do we use to do stuff? ATP, adenosine triphosphate, right? And then we have different bioenergetic systems to help create ATP, which would be what? Glycolysis is one of them. We have fast and slow glycolysis, depending on what? Type of exercise, but more so like what? Like the type of exercise is important, but intensity of exercise, right? And that's going to dictate like which kind of the spectrum you go towards. So we have glycolysis, and what else do we have? Sorry? All right, we have the Krebs cycle. We have like the oxidative system, right? And that would be the most or the least intense? Least intense exercise, right? What you're doing right now is probably going to be primarily, using the oxidative system, right? Because we don't need anything more than that. And then the last one would be what? Creatine phosphate system, right? Which we use what for energy? No, just creatine, yeah, right? So creatine source. A little bit off topic, but it's why we start to get into, what kind of supplements we take and how that helps certain systems and what that is, right? So when we take creatine, for example, we increase our stores and increase our capacity to utilize that system, right? On top of other benefits like brain benefits and these kinds of things. If you're not taking creatine, you should be. You and your grandmother should be taking creatine. Anyways, the purpose of today's lab is to, one, introduce definitions, techniques, and equipment used to assess different cardiorespiratory performance measures, and also learn some common ergometers, including stationary bikes and treadmills, and what they are, how we use them, how we calibrate them, what kind of measures we get from them, these kinds of things. Cool. Some key definitions, right? The first one being force, right? Force is a physics-based metric, right? And it's identified as mass times acceleration, right? So units for this can either be in pounds, kilos, kiloponds, newtons, and understanding that 1 kilopond is just 1 kilogram under Earth's gravity, so a different component from this. We're going to primarily be using kiloponds when it comes to like the bike ergometer. So if you've seen like the Monarchs in the other room, like that's kind of what we're talking about there. All right, so force. What I do want you guys to start to understand is all of these are connected in some sense. Yeah? Just keep that in mind as we go through them, because you're going to see, like, for example, force. Sorry, I have things up for sale. And like, it's one of those like PTSD sounds, and it's like, you start to like check and see if you make money. Yeah. Okay. So remember force, right? Guess what? Work. Now we have work. And look what's in that equation. Wow. Right? So we know that these things can be dissected a little bit more, right? So if we know that work is force times distance, this can all, like, right or wrong, can this also be shown as work is equal to mass times acceleration times distance, right? So this is when we start to be able to understand how to find things if we only have certain measures and be able to quantify in different ways, right? Units for work are Newton meters or in joules, right? An example being a 150-pound person stepping up a 3-foot bench, right? You do one times the other, and we're able to get 450 foot-pounds, right? So a lot of times when we use work, when we think about force times distance, we can use this for a few things in, our field in respect more so to, I like to use it more so for like training load management. So if I know I want to like accurately track someone's work throughout the week, right? I can have an idea, and you might need a few different pieces of equipment to do this, but if we have like a force measure, we have a distance measure, we can quantify someone's work, right? And so when we're looking at like acute to chronic workloads, right? Acute to chronic workload is just training load management. So if I have someone that I'm, for example, training, and I want to make sure that I'm not increasing his risk for injury by like overworking him, I have to track his training load, right? And there's different ways to do that, and one way to do that is to track their work, right? So they work over time, these kinds of things, and understanding like what that looks like from a week-to-week basis and being able to control for that. So just another measure that we can use that, a little bit more of an applied measure to use. Then we get into power, right? Power is probably one that everybody's heard of in some way, and this is another quantifiable measure that has units to it that we can actually quantify. All right, so there's two ways that we can quantify power. I say that, but again, all of these can be dissected into further formulas and used however we want, right? And then obviously you can transfer over a little algebra. Yeah, so power can be shown as work over time or force times velocity, which is probably going to be your biggest formula you see, one of the biggest formulas you see in this field in general, from a strength conditioning sports science standpoint, right? Force times velocity, we have like the force velocity curve, a lot of these things that people like to glorify for whatever sense, just because power is inherently going to be one of our biggest key performance indicators in sport. For example, like if I told you I want to make this guy less powerful, like you'd probably think I'm out of my mind, right? Same thing if I want to make, like I want this guy to be slower, I want this guy to be like weaker, right? Like that doesn't make much sense, right? An example, or I guess the unit for this would be watts, which is equal to 1 joule per second, right? So it's very important to understand that with power, there is always going to be a rate component, right? There is a rate component, some sort of a time component, right? Something per second or something along those lines, yeah? An example of this being a 150-pound person stepping up a 3-foot bench every 5 seconds, right? So we're adding, right? We have before, which was just work, and now we have a time component, right? So work over time. Yeah, and the power for this would, for example, be 90 foot-pounds per second. And then power for cycling is often expressed in kilograms per meter per minute, or kilogram meters per minute, so kpms per minute, just because we have, for example, the belt that we know have a known distance, and we have cadence, so we have like some sort of a rate component, and we're able to quantify power outputs over time. It's one of the reasons why when we test on the bike, a lot of times it's more, the word's not efficient, but we can get more from it because the work is more standardized compared to someone on a treadmill. What do you think would be the differences if I had someone do a test? Let's say a few different people do a test on a treadmill versus on a bike, one of the ergometers. What would be the difference? I might not be wording that correctly, but what could be different for somebody on a treadmill versus on a bike? Form, right? So we have different forms. What else? What's the most obvious thing? Okay, right? So we have a weight-bearing component and a non-weight-bearing component, also very important. Yeah? What else? Why is it harder to standardize a treadmill-based assessment? What's not standard amongst people? Stride length, which means what? Or what's different? I know, I get that, but like, what dictates stride length? Biomechanics, right? Biomechanics, we have what else? Like, what's the difference between you and you? Or you and you? It's the most obvious one. You're taller. You have longer limbs, yes. Right? So, a specific speed for you is going to be probably easier than it is for her, just because your stride length is longer, which means your stride frequency is going to be shorter. Or, sorry, yeah, it's going to be less. Like you're going to have a lower stride frequency versus you, who have to take more steps to maintain that same speed. Versus on an ergometer, it's a set distance, so to say. The only thing different would be the height of the seat. But at the end of the day, like the belt is going to be 6 meters the whole way through, and there's, not necessarily like, I wouldn't say cheating that, but it's going to be standard the whole way through. All right. So when we're doing tests and stuff like that, these are kind of the things that we think of. Now, unless it's like a self tests where we're doing it only on ourselves and it's just an overtime thing. That's obviously different. But when we're doing it against the population or against the means of a population, there's things that we have to keep in mind for that. Makes sense? All right, so a little bit of differences, which we'll get into later also in this presentation, but just differences between like a bike ergometer or a treadmill ergometer or even like a rowing ergometer, different ergometers and what we're thinking about when we're choosing test selection and what we're actually looking at. Yeah? Okay. So power. Power is probably going to be the most important metric in this field, right? You will always hear power. Next, right? So we have a metabolic equivalent of power, right? So when we think about the metabolic aspect of it, now we're thinking about like gas exchanges and different things along those lines and what that looks like. So this is known as the rate of energy expenditure that occurs for a given task, right? So how intense an activity is and what we need metabolically to perform that activity, right? Because again, there's also a rate component here and there's an intensity component here. Absolute VO₂ for non-weight bearing activities, and we use relative VO₂ for weight bearing activities, right? The reason why we use absolute is because, well, the reason why there's a difference is because for one, weight's going to be a big component versus the other, which it's probably not, which would be the absolute situation in this compared to, let's say, bike and treadmill. Absolute would be for which one? The bike, right? It's a non-weight bearing component and it's not going to make much of a difference, right? Versus the treadmill, which, you know, weight does make a difference. All right, now we get into a little bit of like stationary cycle ergometry and what that looks like, right? So we talk about the Monarch. The Monarch is going to be one of the most popular ones in this field. There's different brands, right? Obviously, there's, you know, a bunch of different bike ergometers. You probably went to the gym and you see all the Lifetime Fitness ones or the Peloton bikes and all these kinds of things. These are all ergometers in some sense. It's just a stationary bike, right? Whatever that looks like. Advantage of these, I wouldn't necessarily say portable, but they are simple. They're very simple machines. They're durable. I wouldn't say low cost. Some of these can get very expensive. Like some of the newer Monarchs are like $20-some thousand. And it is very easy to collect physiological data because the person is stationary in place. And if you're going to use gas exchange analysis, for example, like a metabolic cart, it's very easy to set that up on somebody. Most people can also perform these assessments. It's very easy to do, right? Depending on the bike that you use, some of them are going to give you more data than others, right? So it just really depends. There are some manually braked ergometers, which are more complicated, which we'll show you what that looks like today. And then there's also electronically braked ergometers, which are much easier to use. And it's kind of like a gold standard. We use those for any sort of research or testing based situation, just because it's much less complicated. Not to say that the other one isn't, it's a lot of work, right? And again, most people can perform these assessments, which is the plus side of it, right? You can get anybody off the street, put them on a bike, and they can just cycle. Like that's pretty consistent. It's designed to accurately measure power production with the frictional force being measured in kilopounds, like I said earlier, and which can also be converted into kilograms at some point. All right, moving on, we get into, you know, work calculation and what that looks like. So we have a certain amount of kilopounds of resistance times 6 meters per revolution, because the length of the belt is always going to be 6 meters, and that's going to be equal to our work on the bike, how much work is done. Then when we calculate power, our work times our cadence is going to dictate our kilopounds meters per minute. Yeah, so that's how we calculate power. All we're doing is thinking about our formula and putting together our different pieces of that formula. Right. This is going to be important for you guys, being able to calculate power from the bike. So it's something that you should relatively understand, and we'll do it over there and I'll show you exactly what that means, right? So if we know what resistance we have and we know our cadence, we will be able to calculate power because we also know the length of the belt, and that's going to be standard across each situation. Right? So long as we know resistance and cadence, we're good, right? Our force component and our rate component. Yes? Good? Questions? No? We convert kpms per minute to watts by dividing by 6.12, but we just round for 6. For the lab. We'll talk a little bit more about the calibration of the bike ergometer, because if I tell you here, you won't really understand what I mean by all of it. It's like if I say detach the belt from the balance spring, you're not going to know what that means unless I show you, right? So we'll move on from that. And then approximating oxygen consumption for cycle ergometry. Again, this is a estimation component, but if we have like the gas analysis or the mask on you, like using a cart, this is all easily quantifiable. But if we wanted to estimate, right, we have our formula here. And then, for example, if we have a 70 kilogram male cycling at 360 kilograms per minute, or kilogram meters per minute, we're able to estimate based on a formula that was produced in some sort of a study. Yep. Now we get into treadmill ergometry. There are, again, like I was saying earlier, there are a lot of complications in measuring work and power due to a variety of different things like grade, running style, movement economy, height, stride length, stride frequencies, injuries, whatever that looks like, because it's a little bit more of a dynamic movement versus just cycling, if that makes sense, right? And it's a simple calibration process because a treadmill only does two things. It does speed and it does grade, right? So we have like how fast it's actually going, and if it's measuring, for example, if I put 3 miles per hour on a treadmill, is it actually going 3 miles per hour, right? Because that's important, right? And then the grade, for example, which is the incline. If I want a 5% incline, is it actually a 5% incline? Make sense? Cool. Same thing for this. Like I can read this to you, but it's not going to make sense unless we actually do it over there. So speed calibration, all we're trying to do is see, again, is this going as fast as it actually says we're going, right? So this would be like a validity situation, right? It can be reliable, right? Because if we use the same treadmill over time, like, and we put 3 miles per hour, even though it's not accurate, it'll probably be the same speed either way. So it'll be a reliable measure for that specific treadmill. It just won't be valid if we haven't, or if we don't know what it is, right? And then grade calibration, same thing, like just knowing that the incline is actually the incline that we're using. And then approximating VO2 for running. Again, these are all like approximations, so to say. But if we have, again, the mask on the person, we're using like true gas exchange analysis, like we should be able to get this measure fairly simply, considering how to use it. But if we wanted to approximate, we would use this formula and then just input the measures. For example, a 70 kilogram male running at a 10% grade and 6.5 miles per hour. We could presume that they're running at X VO2. Right? Or that's the specific intensity that we're approximating for, right? And that's going to be very different for each person. References and cool. Cool. Any questions on this? No questions? Okay, we're going to go next door now and talk about it some more.